Compute the integral using appropriate substitutions. Use arc notation, do not raise to the negative 1 power. So here we have the integral of e to the t over the square root of 1 minus e to the 2t dt. Now, the things that you might try here, like for instance, u substitution. You could try using u substitution and let u equal 1 minus e to the 2t, because du here is similar, but du is going to be, the derivative of a constant is 0, so this would be negative e to the 2t because it's itself times the derivative of the exponent. So the problem here is I would still need an e to the 2t in the numerator, but I don't have e to the 2t, I just have e to the t. So u substitution is not going to work here. So we'll eliminate that possibility and try a different way. Logarithmic integration, what we would need is the numerator to be the derivative of the denominator. And certainly that's not the case because the derivative of the denominator would use the chain rule and it would get very messy. So the only things that we have left here for square roots in the denominator are the arc-trig functions. So looking through the arc-trig functions, we need to just identify which one might fit the form best. So certainly the arctangent is out because it doesn't involve any square root in the denominator, so that's no possibility. Arcsecant is sort of possible because we have a function on the outside, but the thing about that is this function on the outside would technically be e to the negative t, and the relationship between u and u squared, what we would need here is u being e to the negative t, u squared would technically be e to the 2t, but the reason that arcsecant doesn't apply is the order of the factors underneath the square root. So it's constant minus function, and arcsecant is function minus constant, so that's out as well. So that leaves us using the arcsine if anything's going to work. So let's try this out. So the first thing that we'll need to do is identify what a and u are. So a comes from the constant underneath the square root, and we know that a squared is equal to 1, so that means a is equal to 1. U comes from the function, so u squared is e to the 2t. I'm writing these steps out because you might not be as familiar with how to take the square root of an exponential as you might need to do in order to do this in your head. So a way of expressing e to the 2t is writing it as e to the t quantity squared. That's completely equivalent to e to the 2t because when you multiply exponents, when you take an exponent raised to another exponent, you multiply those. So you can just decompose them as well. All right, so what that means is if I take the square root of both sides of this, u is e to the t. Okay. Now, what also has to match up here in these problems is du. So I can only have 1 times du in the numerator. So let's see what happens. So du, the derivative of this substitution, is going to be the derivative of e to the t is itself times the derivative of the exponent, so e to the t dt. And that is exactly what I have right here in the numerator. So we're good. We're all set here. So this effectively changes us into the form, the integral, and I'm going to do all the steps here. So this would be 1 over the square root of, so a is the 1, so that we're just going to write that as 1 squared minus u, which is e to the t, so minus u squared. Du is equal to e to the t times dt, so this is du. And so that is exactly the form that we need in order to evaluate this integral. So our integral then becomes arcsine, and it's u over a. U is e to the t, a is 1, so it's just e to the t, plus c. Now, last thing is when you answer, it does say here to use arc notation and don't raise to the -1 power. However, that's an antiquated thing. You can actually put your answer in as, oh, sorry, not the arc. So as sine raised to the -1 and then put e raised to the t. That's fine. You'll get the correct answer. I personally think that it's easier to write things like arcsine, and it doesn't look as lofty. That sine to the -1 just looks really weird to me. Either way will work just fine.